Speed of light. The speed of light in vacuum, commonly denoted c, is a universal physical constant that is important in many areas of physics. Its exact value is defined as 299,792,458 meters per second, approximately 300,000 kilometers per second or 186,000 miles per second. According to the special theory of relativity, c is the upper limit for the speed at which conventional matter, energy or any signal carrying information can travel through space. On an average, sunlight takes about 8 minutes and 17 seconds to travel from the Sun to Earth. This also means we are seeing the Sun of 8 minutes 17 seconds ago. All forms of electromagnetic radiation, not just visible light, travel at the speed of light. For many practical purposes, light and other electromagnetic waves will appear to propagate instantaneously, but for long distances and very sensitive measurements, their finite speed has noticeable effects. Starlight viewed on Earth left the stars many years ago, allowing humans to study the history of the universe by viewing distant objects. When communicating with distant space probes, it can take minutes to hours for a message to travel between Earth and the spacecraft. In computing, the speed of light fixes the ultimate minimum communication delay between computers, to computer memory, and within a CPU. The speed of light can be used with time-of-flight measurements to measure large distances to high precision. O. Roemer first demonstrated in 1676 that light travels at a finite speed, non-instantaneously, by studying the apparent motion of Jupiter's moon Io. Progressively more accurate measurements of its speed came over the following centuries. In a paper published in 1865, James Clerk Maxwell proposed that light was an electromagnetic wave, and therefore traveled at the speed c. In 1905, Albert Einstein postulated that the speed of light c with respect to any inertial frame is a constant and is independent of the motion of the light source. He explored the consequences of that postulate by deriving the theory of relativity, and in doing so showed that the parameter c had relevance outside of the context of light and electromagnetism. Massless particles and field perturbations such as gravitational waves also travel at the speed c in vacuum. Such particles and waves travel at c regardless of the motion of the source or the inertial reference frame of the observer. Particles with non-zero rest mass can approach c, but can never actually reach it, regardless of the frame of reference in which their speed is measured. In the special and general theories of relativity, c interrelates space and time, and also appears in the famous equation of mass-energy equivalence, E equals mc squared. In some cases objects or waves may appear to travel faster than light, e.g. phase velocities of waves, the appearance of certain high-speed astronomical objects, and particular quantum effects. The expansion of the universe is understood to exceed the speed of light beyond a certain boundary. The speed at which light propagates through transparent materials, such as glass or air, is less than c. Similarly, the speed of electromagnetic waves in wire cables is slower than c. The ratio between c and the speed v at which light travels in a material is called the refractive across the Milky Way 100,000 years from the Andromeda Galaxy to Earth 2.5 million years index n of the material, n equals c/v. For example, for visible light, the refractive index of glass is typically around 1.5, meaning that light in glass travels at c/1.5 is almost equal to 200,000 kilometers per second, 124,000 miles per second. The refractive index of air for visible light is about 1.0003, so the speed of light in air is about 90 kilometers per second, 56 miles per second, slower than c.